Okay, so I think with the chemistry practical out of the way, I think it's a very good time to go through a planning question that came out last year. So this planning question is from 2022. Okay, so for this planning question, we have this student claiming that time t equal to kd over r square. So where d is the distance that the blue tag move and k is a constant for this oil. So we are to plan an experiment, right, to show that whether the student claim is correct. Okay, so with this, maybe I just show the context. Okay, we are asked to drop a blue tag through this oil. So of course, the time that the blue tag take to move from this point all the way to the bottom, right, that will be the time. So let's just say I draw a stopwatch. This is the t. So what is the d and r? So if you look at the d is just the depth of the oil, and r is the radius of the blue tag. So if you recognize one thing, right, we have two independent variables. So normally, in a normal physics planning question, we are only given one independent variable and of course one dependent variable. So a very classic example is like, for example, t square is equal to k L square. So t is your period. So t square is your period square. L is the length of the pendulum. L square is the length square of the pendulum, where k is a constant. So obviously you can see that your L is your independent variable. For your t is your dependent variable. But looking at this formula, right, you can see that t, of course, t is the time taken, right? So this is your dependent variable. What about d and r? So d is 1, the first independent variable. So this independent variable. So the second independent variable will be your r. Okay, so of course for k will be the constant. So how do we go about to do this experiment? So of course, let's look at what should we include in our plan. So they say in your plan you should identify one other key variable, describe how you would perform the experiment, sketch the graph that you would obtain if the suggested relationship is correct, and last but not least, explain one precaution that you should take to ensure the accuracy of the experiment. Okay, so same idea, always use the idea of VIP. So V, I, P. So V is your variable, meaning it's the dependent variable, independent variable, and of course don't forget your control variable. I is the instrument to measure your variables, and of course P will be the procedure. Okay, so let's take a look at the first part. Okay, so for the first, right, of course if we are given two independent variable, we can only vary one first, meaning that, okay, for example, I vary the depth of oil, so I vary the d, right? So dependent variable will be the time for the blue tag to travel through the oil. Okay, what are the constant, meaning the control variable? So minimally you try to write two. So of course the first one will be the radius of blue tag, because I change the depth of the oil, meaning that I must keep the radius of the blue tag constant. The second will be the temperature of the oil. Why? How do I know the temperature of the oil will be one of the controlled variable? Because apparently, right, last year the question 2, the very first part, they actually asked us to measure the temperature of the oil. So this is a very clear indication that actually temperature of the oil will affect the so-called the viscosity of the oil, or what we call the density of the oil. Yeah, so these are the two control variable. If you have more control variable, feel free to write down. But minimally, you must write two control variable. Okay, so now let's continue on. Okay, so after we are done with the V, we will go to the procedure. So the procedure first, set up the experiment as shown, measure the radius of the blue tag using the vernier caliper. You can use the analog vernier caliper or what we call the digital vernier caliper. But apparently for this step number 2, try not to say measure the radius, try to say measure the diameter of the blue tag using vernier caliper. And how do we get the radius of the blue tag? You simply just use the diameter divided by 2. So it's good to say that, for example, you say that, measure the diameter of the blue tag using vernier caliper, which is the instrument that is used to measure the so-called the variable, right? And record as big D. Yeah. Then you must also tell them how do you get the radius. So radius can be calculated using d divided by 2. Okay, so point number 3, pour oil into the measuring cylinder and measure the depth of the oil using half a meter rule. So this is the second instrument, right? But this instrument is used to measure the independent variable, which is shown here. So this is an independent variable, meaning that I'm going to change later after I get the first data set. Okay, record the depth of the oil as D1. Okay, so step number 4, drop the blue tag and start the stopwatch simultaneously. Record the timing as T1. So you can see, right, for the stopwatch, this is the second instrument, but this second instrument is used to measure the independent variable. Right? Okay, so you record the timing as T1, but you must also repeat the experiment. Because, for example, right, if you are dealing with time, so you are dealing with stopwatch or time, right, or period, whatever lah, you must always repeat the experiment minimally 2 times. So you must say, repeat the experiment for the same depth and record as T2. How do I calculate the average time? I simply just use determine the average time, bracket T, right, by using T1 plus T2, the whole thing divided by 2. Yeah. Okay. So step number 7, you say increase the depth of the oil by pouring more oil. You can just say increase the depth of the oil. Yeah, but I think it's a very good habit to say increase the depth of the oil by pouring more oil, because you are telling the examiner that you are pouring more oil to increase the independent variable, which is known as the depth of the oil, and record as D2. Repeat step 4 to 6. Then the last step, right? Repeat step 3 to 7 for different depth of oil and get a total of 6 data set. Yeah. So this is the procedure. Okay, so now let's move on to the analysis, which is the most important part. Okay, analysis, you must say plot something against something. So plot T against T, because for the D, right, the depth of the oil is the independent variable. Then for the big T is the time for the blue tag to move through the oil, right, is the dependent variable. So you're actually plotting T against D. So of course, if I go back to the formula, right, so it's T equal to K D over R square. So this is your big Y. This small d, right, is your big X. So you can see that there's an expected gradient of K over R square. So this is your gradient and an expected Y-intercept of 0. Or you can just say pass through the origin. Yeah, so that is the analysis part. But don't forget to add in one more thing, or to draw one more thing, which is the graph. So for example, you draw the graph, you draw the axis first, then you draw a straight line. But this straight line, just take note, must pass through the origin, and you must add in a 0 here. So the y-axis you put big T, the x-axis you put small d. Yeah, so that is what they are looking out for. So that is the very first part. Now, of course, if I go back to this formula, so apparently we are done with the first independent variable. What about the second independent variable? So it's the R, right? So that's where I need to go to the experiment 2. Yeah, so experiment 2 is right here. Okay, experiment 2 is where now instead of varying the depth of the oil, I want to keep the distance of the oil constant. So now what do I vary? I vary the radius of the blue tag, meaning that maybe I start from 1 centimeter, the radius of blue tag to be 1 centimeter, I slowly increase to 2 centimeter, 3 centimeter, so and so forth. Okay, so now the independent variable will be the radius of the blue tag. The dependent variable will still be the same, which is the time for the blue tag to travel through the oil. So what are the constants now, or what we call the control variable? First will be the depth of the oil. Second will be, again, the temperature of the oil. Okay, so let's go to the procedure now. Okay, first set out the experiment as shown. Okay, second, measure the radius. Same thing, you put down the diameter using vernier caliper, record as R1, or what we call D1. Okay, maybe I just write down. So measure the diameter and record as maybe big D, and the radius, right, will be equal to D divided by 2. So pour oil into the measuring cylinder and measure the depth using half meter rule. Record the depth of the oil. So number 4, drop the blue tag, right, and start the stopwatch simultaneously. Record down the timing as T1. So you can see for step number 4, step number 5, number 6 is roughly the same as the experiment 1. So number 7, okay, so step number 7, you must say, increase the radius of the blue tag by using more blue tag and move it into a spherical ball. So measure the radius of the blue tag again using the vernier caliper. So all these underline, right, they are known to be your instrument, because it's also important to write in the instrument that you use to measure the variables. So record as R2, repeat step 4 to 6, and of course last but not least, repeat step 3 to 7 for different radius of blue tag and get a total of 6 data set. Yeah, so step number 8 actually is very important. You must say you must get a total of 6 data set. Okay, now let's move on to analysis again. So now we are not plotting T against D. We are plotting T against 1 over R square. So why do I want to plot 1 over R, T against 1 over R square instead of maybe T against R? Because if you plot, for example, right, T equal to K D over R square. If you plot T against R, right, your graph will look something like this. Yeah, so it's like y equal to 1 over x square graph like that. So what I want to do is actually to linearize the graph. So how do I linearize? Very simple. So you just need to put T equal to K D first. Then you, of course the R square, just put 1 over R square. So this whole thing here will be big Y. This whole thing here will be big X. So of course this thing here will be your gradient. So it's a y equal to mx. So plot T against 1 over R square with an expected gradient of KD. So you must tell them what is the gradient, and you also must tell them what is the y-intercept. So they say expected y-intercept of 0. Or you can just say pass through origin, doesn't matter. Same idea, you must sketch the graph. For example, how do I sketch the graph? You plot T here. Of course, you plot 0 here, and you plot 1 over R square here. Alright, okay, so that will be the 2 experiment. So with this, I will move on to the reliability. What is reliability? Reliability just means what are the steps that I take, right, to ensure or minimize error. Yeah, so because if I go back to the first part, the question, right, okay, let me just go back. Okay, look at the question. There are 4 points, right? So explain one precaution that we must take, right, to ensure the accuracy of the experiment. So what are some of the precautions? You can write more than one, because sometimes you write one, right, you might not hit the point. You write more than one, high chance is that, okay, minimally you write 3, high chance is that one of it will hit the point. So that is one of the exam technique you can actually implement. So now I go to this point. Okay, so I go back to this reliability. Okay, so for the first reliability, right, you can say, when dropping the blue tag, right, ensure no force is applied to the blue tag, meaning that you just drop it. You don't apply any force to the blue tag. Because if you apply force to the blue tag, you're actually giving it some initial speed. When you give it some initial speed, right, the time taken for the blue tag to travel through the oil actually will be smaller or be lower. So this will actually affect the accuracy of the result. So that is the first one. Okay, second one, you must say ensure that the blue tag is traveling. When the blue tag is traveling through the oil, it does not make contact with the walls of the measuring cylinder. Because if you are doing the experiment, if you are doing this experiment yourself, right, sometimes you realize that, for example, okay, this is the cylinder. So this is the oil. So the oil is here. So this is the thing. Okay, when you drop the blue tag, sometimes you realize that the blue tag is actually like, sliding through the walls of the cylinder. So you don't want to do that, because when the blue tag is making contact with the walls of the cylinder, right, this will actually increase the time taken for the blue tag to travel through the oil. So what I want to do is actually to make sure that the blue tag is in the middle. Then you drop it, right? So the blue tag will just flow through the oil and go to the bottom of the measuring cylinder. So that is another reliability that you can put down. So you say, ensure that the blue tag is traveling through the oil. It does not make contact with the walls, because this will actually prolong the time needed for the blue tag to travel due to the greater friction. Yeah, so that is how we do this planning from last year. Especially if if I go back here, especially if you are given two independent variable, try if time permits, of course. If time permits, right, try to put down two experiment. But if time does not permit, never mind. You just put down one independent variable. Yeah. No, because 6 marks, I believe that they are not too stringent about that. But if time permits, please put down two independent variable, and of course one dependent variable. Alright, so that is how we approach this planning question from last year. And of course, for those who are taking physics next Monday, I wish you all the best.